Okay, so now the only thing we need is to redefine time, and then we can explain some of the mysteries in quantum physics and relativity that we talked about before. But even in this video, we're going to see very interesting new things. For instance, we will derive the constant speed of light instead of using it as an assumption. How's that? And also we'll explain what happened before the Big Bang and why the universe is not infinite, and also why space-time is discrete. It's crazy. Okay, well, let's not get ahead of ourselves. Okay. Okay. Let's have a look again, at simultaneity as defined by Albert Einstein when he, explained to us the special relativity thing. Einstein's made some assumptions, as you remember from previous videos. In order to build our model, we need to start with some basic assumptions, and then from there we can derive everything else. Okay, almost everything else in the case of Einstein, and for that we need independent assumptions. So the first assumption was light or electromagnetic waves in general travels isotropically. What that means? Well, it means it's same thing in all directions. They will go same speed, some whatever. And that's, remember, we need a reference. So relative to a Galilean frame of reference. A Galilean frame of reference is a frame of reference with no acceleration. If you need more details on that, you can go watch my other videos about special relativity mystery. It's a good one, with twins and triplets and everything. Wow, exciting. But anyway, that just means, it goes at, linear constant speed or doesn't move depending on which reference you take, but at least there's no acceleration. Okay, so that's one first assumption. The next assumption was there's no privileged Galilean frame of reference. So in other words, you can take any frame of reference, provided it's Galilean, then you will be able to measure exactly using the same rules for to measure everything. Okay, and you won't find a difference. Well, you will find difference maybe, but the rules will be the same. Constant speed of light. Okay, so that was one of the assumptions here, which actually caused problems to the physicists at that time, because they were measuring the speed of light, and whatever reference they would take as a frame of reference, they would find always the same speed, and we'll see why that is a problem. And finally, he defined time from that, because that was a whole goal, He defined time using clocks and simultaneity concepts. Okay, fine, that's what Einstein did. Now, let's see what we can do from that. Again, we're going to take the same assumptions, light travels isotropically, no privileged Galilean frame of reference, the time defined using clock and simultaneity. No. First of all, we're going to remove this requirement, okay? Interesting. Quite a big deal. And also, instead of using clocks and simultaneity, we don't know what clocks means actually. We'll use space because we have defined what space is, and how we measure it, and therefore we can do that now to define time. So how are we going to do that? Well, it's not very complicated actually. Let's take an example. We use a car here, the blue car, which is of length b minus a. But if, to simplify things, we'll say A is equal to 0, therefore the length is equal to B. Okay. It's at rest viewed from the Earth. Okay, it doesn't move relative to the frame of reference here. Now, let's suppose that inside the car, there's a guy firing a bullet, that goes from A to B inside the car. Okay, like this. Beam. Okay. Now, simultaneously, and we know what that means because we have defined simultaneity before, simultaneously to the bullet, we send a light ray from A to D here, such that the light ray reaches D simultaneously, and again we know what that means, with the bullet reaching B here. So this looks like this. This is so fun. Okay. And then, by definition, we'll say that the space-time event B the space-time event bullet arriving at B occurs at time D, assuming A is equal to 0, and the time duration taken by the bullet to go from A to B is the spatial distance, here, equal to D. That will be our definition of time. So time in that case is actually a spatial distance, space distance. And we know what this is because we have defined space before. So that's quite interesting. The other thing interesting is if we look at the speed, of the bullet. Well, it would be like in classical physics, speed is equal to the distance, which was b, divided by what we call the time here, which is d. So the speed of the bullet in that case would be b over d. Okay, interesting. Now, the bullet speed viewed from the Earth is equal to b over d. That's what we just saw. The bullet speed viewed from the car, since the car is not moving, is the same, b over d. So it's equal to u1. Now, if instead of a bullet you send a light ray, then b is equal to d. Okay, so you get u1 is equal to b over b. And of course, u prime is also equal to b over b. That's equal to 1. So the speed of the light ray will always be the speed of a light ray from any Galilean frame of reference, which is equal to 1 in that case. Okay? Interesting. Okay, now let's see what happens if the car is moving. Okay, still in a Galilean way. In other words, constant speed, linear movement. So we suppose that the car, which is here, will move to the right, while the bullet and the light ray travel from A. Okay? Beam. Wah, This is funny. Now, what happened here? Well, first of all, the bullet speed viewed from inside the car is still the same. The guy inside the car has no way to know what's happening, and in any case, if he measures the bullet speed, will still find the same value as before, which is b over d. Okay. Now, the bullet speed viewed from the Earth is now, by the definition we gave, is equal to c, because viewed from Earth, the bullet came from A to C, which is 0 to C. And the time, as defined, like we did before, is equal to E. Okay? And therefore, the speed viewed from the Earth would be C over E. And notice that instead of a bullet, if we send a light ray, then C will be equal to E, and therefore the speed of light will be equal to 1 again. So that means that it will be the same for any moving frame of reference, Galilean frame of reference. So with using just a definition, we derive in a trivial way the constant speed of light. And this is what I say here. And I'll explain with more detail what's happening in the math-oriented video series. Now, let's make some final comments. So, to summarize, with this definition of time, we can trivially derive the fact that light speed does not depend on a frame of reference, while special relativity uses that as an assumption, a building block. And we don't need clocks. Clock was just introducing more complexity, and if you wanted to be really, pinpointing details, and then it's better. Here we don't need clocks. We just used our definition of space and time, and we were able to derive this constant speed of light. And with this definition of time, we can still apply all results from classical Lorentz formulas, except here we'll use C equal 1, which is what physicists today do a lot, just to simplify calculations. But they just use it as a mathematical trick. Here we showed that in our definition, C is actually equal to 1, always. Okay, all the above assumed, of course, that we could precisely measure space, and which is what we did before. We explained very carefully and precisely how we would measure things in space, and therefore space itself. Now, why do we use light, to define simultaneity, as we've seen before? We could have used something else. We could have used sound, or we could have used, I don't know, many different things. But the advantage of using light here is that, first of all, we don't need a medium. Like, for instance, if you use sound, well, you need air, and if you don't have air, then you cannot define simultaneity, and therefore you cannot define everything we've defined so far. Second thing is that, well, light is isotropic, okay, so that's part of our assumptions, and it's very fast and very precise because it's very fast, so you can really be very, very accurate, and in particular, what my feeling is that because of Pauli's exclusion principle, which is not applicable to bosons, that means that two photons can be at the same time at the same place, same position. And therefore that allows you to give an extremely high precision for the position, and time and all the rest that we've seen before, But that has an implication, of course, which is that space-time is discrete. It depends on the photons. And there are also, with what we've just seen, there are other implications. When we ask, what happened before the Big Bang? But before the Big Bang, there was no light. Remember, we're talking about the physical world here, not the reality world, which we never know anything about. And so it has absolutely no meaning. It's like if you ask, how long does it take a cat to fly a distance of 1 kilometer? Well, cats don't fly, so your question has no meaning. Well, it's the same here. Okay, so what happened before the Big Bang? Well, nothing, because it doesn't mean anything. Okay, and now what about the size of space? Well, as we've seen, in order to define space, we need matter. So as soon as you have no matter, there's no space. Okay, so I guess the limits of our universe today are the limits of where we have matter, and that's it. Crazy.